Okay, so today we're going to be doing a think aloud on this article, which is entitled Water, Properties and Behavior by Anthony Carpi. And so let's just do a quick walk through this article. It's going to be 6 pages, and I've sort of highlighted some of the particular sections of this article. So we're going to start with the Did You Know, which is sort of a question or a hook that the author is going to use to bring us into the information. And then there's a bit of a summary here, some terms that we should know, and we'll go through, and we're going to be talking about water as a solvent, the polarity of water. We're going to be speaking about hydrogen bonding and the arrangement of water both as a liquid and as a solid, which is ice. We're going to talk about surface tension. We're going to speak about the basilisk lizard, which is also known as the Jesus lizard. There's a couple of comprehension checkpoint questions that we're going to be responsible for. And then we're going to speak a little bit more about water as a solvent and how it reacts around charged particles or ions, such as sodium and chloride. Okay? And then I've got a few things that I'm going to want you to take down in your ISN once we're done with this Think Aloud. So let's go back to the start and let's work our way through this. So did you know that the way water molecules interact with each other caused the sinking of the Titanic? And the unique chemical properties of this miracle liquid that cause icebergs to float also cause the surface of water to stick together with enough force that the basilisk or Jesus lizard can walk on water. That's very interesting. I'd like to know more about how that lizard can walk on water. I've heard of this lizard before, but I don't know exactly how that works. So here's our summary. Water, critical to our survival, behaves differently from any other substance on Earth. The unique chemical properties of water are presented in this module. The module explains how the dipole across the water molecule leads to hydrogen bonding, making water molecules act like little magnets. Also explored are surface tension and water's properties as a solvent. So as I read that, I'm reminded of this word dipole and what that means. So we're going to just sort of put a little bit of a question mark here and see if we answer this question as we go along. So here's 3 terms that we're going to be dealing with in this article. Bonding, which is the act of fastening 2 atoms together. Covalent, which is a type of bond that involves the sharing of electron pairs between atoms to achieve chemical stability, as is with the hydrogen and oxygen atoms that make up the water molecule, and also solvent. And the author here describes solvent as the substance present in the greatest amount within a solution. But I always like to remember that the solvent is what does the dissolving. Okay, so I'm going to ask you to jot that down in your version of the article. Please jot down that the solvent is what does the dissolving. And also you notice I have a little note here for your ISN. So go ahead and write that in your margin as well, because you're going to be coming back to that later in your homework assignment. Okay, so in many ways water is a miracle liquid. It is essential for all living things on this planet at least, and it is often referred to as the universal solvent because many substances dissolve in it. These unique properties of water result from the ways in which individual H2O molecules interact with each other. So here's the sketch that the author has included in the article, and I've just sort of redrawn it here so that you can see what it looks like. And this red is the oxygen, and the 2 green ones represent the 2 hydrogen atoms that are attached. And if we wanted to see that in 3 dimensions, then here would be your oxygen, and here would be the 2 hydrogens that are attached with these 2 gray pieces which represent the covalent bonds. Okay, so I'll just set that right here. In the chemical bonding lesson, we discussed the dipole. Here's that word again that we were wondering about. That forms across the water molecule as a result of the polar covalent bonding between hydrogen and oxygen. See our chemical bonding module. Okay, we might come back to that later. Because of the bonding, electrons are shared unequally by the hydrogen and oxygen atoms. A partial negative charge, which is this swirly line with a negative sign, a partial negative charge forms at the oxygen end of the water molecule. So over here on the oxygen, we know it's going to be partially negative. And a partial positive charge forms at the hydrogen ends. So we know that the hydrogen is going to be partially positive. Since the hydrogen and oxygen atoms in the molecule carry opposite charges, nearby water molecules are attracted to each other like tiny little magnets. The electrostatic attraction between the partially positive hydrogen and the partially negative oxygen in adjacent molecules is called hydrogen bonding. And we're going to see that on the next page. So here we see hydrogen bonding in between 5 water molecules. Hydrogen bonding makes water molecules stick together. And when I read this, it makes me wonder, are hydrogen bonds as strong as covalent or electron-sharing chemical bonds? So let's read on and see if we can explain whether or not hydrogen bonds are as strong as covalent bonds. While hydrogen bonds are relatively weak compared to other types of bonds, they are strong enough to give water many unique properties. For example, hydrogen bonds sank the Titanic, and hydrogen bonds allow the basilisk lizard to walk on water. As a result, the basilisk has earned the nickname Jesus lizard. So just how does hydrogen bonding do this? Well, let's start with the Titanic. The Titanic sank because it hit an iceberg, a chunk of ice floating on the surface of the ocean. The reason ice floats is because of hydrogen bonding. In water's liquid form, hydrogen bonding pulls water molecules together. As a result, liquid water has a relatively compact, dense structure. The animation below illustrates this idea. So I've circled this and I'm emailing you a Gmail link. So please check your Gmail accounts. And also we have a note here about our ISN that you'll want to jot down quickly. Okay. As water freezes into ice, the molecules become frozen in place and begin to arrange themselves in a rigid lattice structure as shown in this animation. So you'll want to view that as a part of your homework time. Okay. And we come to our first comprehension checkpoint. So it's asking us water molecules are attracted to each other because of A, oxygen bonding, or B, hydrogen bonding. And you'll jot that in your ISN. As we just discussed, neighboring water molecules are attracted to one another. Molecules at the surface of liquid water have fewer neighbors and as a result have a greater attraction to the few water molecules that are nearby. This enhanced attraction is called surface tension. It makes the surface of the liquid slightly more difficult to break through than the interior. Surface tension. When a small object that would normally sink in water is placed carefully on the surface, it can remain suspended on the surface due to the surface tension. The basilisk lizard makes use of the high surface tension of water to accomplish the incredible feat of walking on water's surface. The basilisk can't actually walk on water, rather it runs on water, moving its feet before they break through the surface. Take a look. And so here's another video that you'll need to view. Okay, we have another comprehension checkpoint. In liquid water, which molecules have a stronger attraction to each other? A, molecules that are on the surface, or B, molecules that are below the surface. So you'll put that answer also in your ISN. The partial charge that develops across the water molecule helps make it an excellent solvent. Water dissolves many substances by surrounding charged particles and pulling them into solution. For example, common table salt, sodium chloride, is an ionic substance that contains alternating sodium and chlorine ions. And here's the picture that you can see that. When table salt is added to water, the partial charges on the water molecule are attracted to the sodium and chlorine ions. The water molecules work their way into a crystal structure and between the individual ions, surrounding them and slowly dissolving the salt. The water molecules will actually line up differently depending on which ions are being pulled into solution. The negative oxygen ends of the water molecules will surround the positive sodium ions. And also the positive hydrogen ends will surround the negative chlorine ions, as shown in the following picture. So here we see that the partial negative ends of the oxygen are surrounding this positive sodium ion. And also if the water molecules turn themselves around, then the partially positive hydrogen side of the water lines up with the partially negative chlorine ion. And that's how table salt is dissolved in water. In a similar fashion, any substance that carries a net electrical charge, including both ionic compounds and polar covalent molecules, or those that have a dipole, can dissolve in water. This idea also explains why some substances do not dissolve in water. Oil, for example, is a nonpolar molecule. Because there is no net electrical charge across an oil molecule, it is not attracted to water molecules and therefore does not dissolve in water. So now that we've completed this article, we're going to discuss it in class, but I want you to staple it into your ISN. And then I also want you to jot down that in your ISN on the output side, the left-hand side, I'd like you to have 2 creative elements. Put in the 3 key terms that we reviewed. You need to have the 2 sketches that we discussed about liquid and solid water molecules. There's 2 checkpoint responses and 2 descriptions and explanations. And as an example, just to give you a bit of inspiration, this is what my output ISN page would look like. So I've got my 2 creative elements, my terms. I need to have a description of how the basilisk lizard walks on water. I also need to describe how water dissolves charged particles. There's my blanks for my comprehension checkpoints, and I have blanks for my 2 sketches that I can complete as homework. So please let me know if you have any questions about any of that before you leave today. Thank you so much.